So yeah, it's 6 o'clock. I started the recording. Now let me share my screen. Yeah, so I think I have shared my screen as well. What we'll do for this class, will hmm, we'll do this slightly differently today. Instead of doing in this PowerPoint, since today's content is more or less focused on the numerical parts of piston cylinder assembly. Uh, we'll try to do it in a notepad. So, anyway, since people are yet to come, I'll start with the introduction slide here. So, this is the week 2 discussion for the course of uh, concepts of thermodynamics. Uh, and today is the discussion for second week of this course. So we'll call it week 2 assignment discussion. And mm, myself, let me write brief introduction here. I'll share uh, this notes with you later. So let me put my name here also. As some of you may know from the previous class, myself Akshay. I am currently pursuing my PhD from Department of Mechanical Engineering, IISc Bangalore. And since this is the PMRF discussion, I'll put my PMRF ID for future reference. So yeah, I think this is a pretty good uh, introduction slide or the first page of your notes for this discussion. So let's oops sorry, sorry, sorry. So now we need to go to the, let's say, next part. So I think this is how it is been done. So yeah, I think I need to symbol it there, and then maybe we can scroll up and down without editing. Okay, so now I'll start with, before that I'll just go up. So yeah, now it's almost 5-6 minutes. Let me check if anyone is there. Yeah, Priyanka is there. Uh, Priyanka, are you able to hear me?
Yes.
And are you able to see my screen also? The notes that I was sharing.
Yes.
Okay. So we'll wait for, let's say, 5 more minutes. Let's say till 6:10, and then we'll start our discussion. Uh, so I'll keep this slide open as it looks pretty good. So anyway, I think you joined slightly late. So today I'm doing this class using the notes instead of PowerPoint slides. The reason is, first of all, this assignment is like more or less dependent on numericals related to piston cylinder assembly. So in PowerPoint, it's difficult because you have a limited space. So to solve a numerical, you may need more space depending on the queries that are asked. So that's why what I've done is, instead of making it into in the form of slides, today I have made it as continuous notes, so that we'll have ample amount of space, and we can not worry about that. And mm, yeah, so this is my first time also doing presentation using notes. So let's hope everything goes well. If you have any problem, like if the font is too small, or if the slides are not properly visible, you can just raise your hand. I can see your hand in my uh, monitor, and then maybe we'll stop and rectify whatever is wrong with the presentation. But at this point, I think the video or the screen is visible, my voice is audible. So yeah, I think we'll wait for, let's say, a couple of minutes, and then we'll start. Last time we waited too long, so actual discussion started by 6:20 and it was 7:20. Still, I could not cover many problems or many concepts that was supposed to be, or that I wanted to cover. So today we'll avoid that. We'll wait for some more time and then we'll start. Uh, yeah, so let's wait for a couple of minutes. Okay, one more person has joined, so I think people are slowly coming. Hmm, the power is gone here. I hope Wi-Fi still works. It may be slow, but I think it should work. Anyway, uh, let's say one more minute and we'll start. Yeah, so we'll start. Let's hope people join. And I hope everyone is able to see my screen and able to properly hear my voice. If not, then please let me know in between. So now we'll start. So before going to the problems of the assignment, let's just first uh, revise what all concepts you learned in the last week. Uh, So I have taken a look at your last week's syllabus of the course, uh, and I could figure out, like, first week was more conceptual. In the last week, from the lectures that I saw on this NPTEL course, I could figure out uh, there were multiple sessions on uh, problems on related to problems related to piston cylinder assembly. Actually, this piston cylinder assembly, it's essentially a uh, closed system. Uh, I mean, at this point, you have not learned energy interactions and all. Maybe that will come in the next week. So at this point, let's just say that this is a system with uh, constant mass, uh, and volume may change, or it may be constant. So so essentially you are studying systems who are having constant mass throughout the number of processes that they undergo. And piston cylinder is a classical example, or template that thermodynamics course has. So if you have seen multiple reference books like Pickenard, Sontag, Moron, and Shapiro, there you'll see, uh, you know, uh, initially when the concepts of thermodynamic cycles or different processes is introduced. Usually, it is introduced with the help of the piston cylinder assembly. So the reason is this piston cylinder assembly represents a constant mass system. Uh, there can be an energy interaction with the surroundings, but that part is yet to be introduced to you in this course. So at this point, you can just say this is a constant mass system in which, uh, like, 90% of the times, the mass between the piston cylinder remains same, or a finite amount of mass can be added. So it's like a constant mass system at any particular time, or at any endpoints of the process. It's not a open system in which there is a continuous flow of mass through the system. So that's why we study this piston cylinder assembly. It is very commonly studied, but you should know why we are studying this, because in the later part of the course you'll move on from piston cylinder to different types of control volumes. So there, piston cylinder is not uh, studied rigorously, because that's not relevant there. Here it is relevant because your focus is on systems who are typically having constant mass at at the end points of each process, you can say roughly. So yeah, so that type of problems were there. And one more concept that I'll briefly introduce here itself. It is related to your uh, assignment also. There are a couple of questions on it, and Professor Chakraborty also gave a quick, uh, in one lecture he introduced it properly. I'll just mention what that concept was if you want to revise it once again. So let's say if this is the TB chart, uh, T is the temperature and V is the specific volume in meter cube per kg. It can be in degree Celsius. We usually use degree Celsius. So the this is phase change line, liquid, vapor, saturation line. So and there will be, let's say, oh, so let's say there is a certain constant pressure line. It should look like this. So it is a constant pressure line, P equal to constant. So and this point is your critical point. So what uh, what the point that I wanted to, or the professor also conveyed, and which is a very critical point for your week 2 assignment, as well as uh, multiple competitive exams and interviews that you may face in future. So let's say you are at this point, uh, denoted by cross and point 1 symbol. So at this point you'll have certain mass fraction, and this essentially represents, if you take a closed system like this, in which you have uh, let's say some liquid plus vapor mixture. So there will be certain level here, there will be liquid, and this part will be vapor. Generally we take air, you can take any other liquid, but this is the general, this is the liquid part. Let me show it by slant lines. So at state 1, x1 is mass of vapor at 1 divided by total mass at 1. But this is a, since this is a constant mass system, your summation of mass will be like summation, it's a sum of mass of vapor and sum of mass of liquid. That will be constant wherever you take this process, as long as it's a constant mass, or there is no exit or entry of another mass in this system. So, and let's say you start heating this system, and it reaches point 2. So uh, what happens is, the intuition that we have is like, if we have a certain system, and if we start heating it, it will boil, or the liquid will be getting converted into the vapor, and then this volume occupied by vapor, it will increase, and the vacuum volume occupied by the liquid will decrease. But that is not true for all cases, and that is exactly the point of this discussion is. So you should remember uh, that when you are to discuss this, we need to first divide our domain of observation into two parts. That's why the critical point is important here. So if your starting point, or point number 1, is in this domain, or if you are on the uh, the right side of the critical point, specific volume here, this will be critical point, or in this case I can write critical CP. So if your specific volume at any stage, let's say at stage 1, if it is uh, here, it will be specific volume at stage 1, and if you start heating here, so since you are heating, the temperature should rise, that is the effect of heating, and your, let's say you reach certain second stage somewhere here, it's still a two phase mixture. It's not a superheated, or saturated liquid yet, saturated gas yet. So let's say this point is 2. So here, your the general intuition that after heating such system, uh, more liquid will get convert into vapor. So therefore, your liquid level inside the container will fall, and your vapor level will rise. So this is our general intuition, but you should be careful on the other region, which is, let's say I'll draw it with the yellow blue line. Let's say if you are at this point, it is, let's say, 1 prime. So this is a different point. You'll have x1 prime, v1 prime. So if you start heating from here, and let's say you heat it till the, let's say, same temperature, and now at this point, see, essentially the logic behind this argument is this length is nothing but uh, which is we call as VFG in steam tables, or VG minus VF. So if you start from the point 1 dash, which is given here, what will happen is your the liquid level, instead of decreasing on heating, it will rise. So I mean, that is counterintuitive, because as I told you, our primary intuition will tell that whenever you heat a liquid, it will evaporate and its level will decrease and the vapor content will increase. But that is true for a general system where mass interaction with the surrounding is allowed. But if the system is closed system, there is if there is no mass interaction with the surrounding, and if you are starting with from this point 1 prime, after heating to state 2 prime, let's say it will be 2 prime here. So there, your liquid level will actually increase and vapor level will decrease. So this was the point, this was the precise point that was conveyed by Professor Chakraborty also. And I am telling you the same point again because it is an important concept. Numericals you'll solve because you have solved multiple numericals in the class. So that will not be an issue for you. I hope we'll solve some numericals also, don't worry. But I thought uh, for the given week's content, this was one of the important concepts that is asked many times in the interview and sometimes in the competitive exams as well. So you should know. And one more point, Professor explained for on the TV plot. If you are doing some calculation on, let's say, PV plot, the same logic holds true also. Here also, let's say if this is the critical point and this is the critical point specific volume. So if you are starting from some point here, you'll end up with the same phenomena that we discussed on the first part here. And if you're starting from somewhere here, you'll end up with the same phenomena here also. So it doesn't matter if it is a PV plot or a TV plot. Essentially, you should remember your starting point and where is the starting point corresponding to the critical point specific volume. Uh, on PT plot, this won't be shown because on PT plot phase change is essentially a point, and there you can't see volume variation. So in that case, you will not see or observe this type of behavior. You cannot observe using PT plot. So it is true for PV and TV. So that is it. And I think there may be some questions in your assignments on this, or maybe uh, later also you can look into this again, and you'll find that it is quite an important concept. So now moving on, I think that was the part related to the concepts this week. Now there are you know, uh, multiple numericals that we'll see. So I think Abhik has already taken like a number of numericals already, but I'll try to do some. I'll not go deeply into the calculations part. I'll tell you how to do it. But since in the last class we discussed about how to use the steam table, and you know, I think you'll be fairly able to solve the problems that are typically asked from this type of questions. Uh, so basically, I'll initially discuss some concepts, and they are pretty common. If you see different problems or different questions from this topic, what I feel is, let's say, what you should know is, mm, first of all, since it's a piston cylinder system, uh, what you should know is, let me draw a thing, like let's say this is that piston cylinder assembly, and the typical problems that you'll see in this domain is you'll have a piston here. Sometimes it can be massless. I mean, massless is a wrong word actually, because it will have some mass. So the correct word should be, uh, it can have negligible mass compared to the uh, volume of, you know, this mixture, or a pure like single phase mixture, or uh, multi phase or double phase mixture, or it will have certain mass, certain finite and comparable mass. So if the first case is there, that the piston is having negligible mass, in that case, if you draw the free body diagram of piston in equilibrium, so yeah, that is one more point. Whatever we are discussing here, it is in equilibrium. And as we discussed in last class, there are three types of equilibrium: mechanical, thermal, and chemical. So no need to go into details of what these three are in the current context, but since there is no energy interaction, primarily we are in the mechanical equilibrium, and mechanical equilibrium is essentially a force balance. And also we neglect friction here, because friction essentially means there are dissipative losses in your system, and you cannot say it is in equilibrium or without any energy loss. So to avoid that type of argument, we generally neglect friction between the piston and walls, cylinder walls. This is the cylinder, this is a 2D cross section, so that's why you are seeing it as like this. And yeah, one more addition will be, you'll have a spring here. It will be attached to the piston. Generally, we study linear springs. That means your force applied to the spring or by the spring will be directly proportional to the displacement or compression or elongation of that spring from its natural length. And one more important thing is, uh, you should be careful in drawing such diagrams, and not to make mistake of closing this whole system. I just showed it using red line, which is shown here. So actually, the point of drawing this piston cylinder assembly with the open edge at the top is to represent that atmospheric pressure is above the piston. If you close this edge using this red line, that means that is not atmospheric pressure anymore, because if your system expands, if this part expands, this will compress and it will be higher than atmosphere, and vice versa. So what I have seen sometimes students do uh, in the in the haste of time is close this edge as well. So don't do that. You just keep this open, so that represents there is atmospheric pressure above the piston. So if you neglect the mass of, let's say, that is also an assumption here. Generally we take P atmosphere above the piston. So essentially you'll see different variations of this problem only in this assignment. So if you know what we are doing here, this is like a synopsis of the different problems that you'll face. And yeah, before going there, I'll just draw the free body diagram of piston. If the piston mass is negligible, in that case, you'll have external atmospheric pressure into area of piston. Uh, since there is no negligible mass, so we'll neglect the weight of the piston here, and there will be certain pressure applied by the this finite volume of single phase or multi-phase uh, domain, which is we generally call it as a system. So that will be the P of the system, and it is also acting on the uh, same cross-sectional area. So it will be also the force will be also P into AP. Since there is no friction, there is no side or circumferential force. And one more thing, if there is a so let's say this is a very you know simplest form of diagram that we can see. So if this is your system which is having negligible piston mass and no spring attached to it, in that case whatever the pressure that atmosphere exerts, the gas or the mixture inside the piston will be also at the same pressure. Now that is not actually a commonly seen case, so we'll draw the free body diagram of a typical case that we usually encounter with. Here we'll have uh, two components. One will be again atmospheric pressure, force applied due to atmospheric pressure, and that will be atmospheric pressure into cross-sectional area of piston. Then there will be some force by the what do you call? It will be by the spring, the interaction between piston and the spring. So that will be given by K delta X. This is the force into area of piston. Now K is a spring constant. Its unit is Newton per meter. Please make sure all your units match. This is the only part where you can do mistake if your concept is clear. Please be careful that your units are there, because generally we take pressure in kPa and we take area in SI units. So you should be careful that your unit of K should be also generally taken in kilonewton per minute, because otherwise you'll miss by a factor of 10 to the power 3 and your answer will be completely wrong. It's not like you'll be in the some ballpark figure near to the answer. You'll be completely off. So please make sure that your units are matched. Then there will be weight of piston, which will be mass of the piston into gravity g, and the force will be divided by the area of piston. Oh, my bad, sorry. So we are since doing the force balance, it will be just mass of piston into g, and then there is our interest or area of interest is the pressure by the our system onto the piston, and it will be again the force will be P into AP. So if you write this summation of forces in, let's say, y direction, if this is our y direction and this is x direction, essentially it is a equilibrium of forces in y direction. So you can simply write PAP equal to K delta X AP plus MPG plus PATM into AP. So this is your typical force balance here, and if you divide the whole thing by a cross-sectional area of piston, you will get okay. I made a mistake here. Here also there will be AP won't be there because it's a force balance we are doing. So essentially, if you divide by cross-sectional area throughout, you'll end up with this factor divided by cross-sectional area of piston plus P atmosphere. And if you understand this equation, I would say 90% of your problems will be solved. Uh, so that's why I'm spending more time of time on this part rather than directly jumping into the problem solving. Here, common mistakes are first, you should be you know check units, because I have seen multiple times people take this stiffness constant on the spring constant unit, which is K in the K delta X expression in Newton per meter, and the pressure is again in pascals or kilopascals. So if they won't match, you'll be far off. Again, the area of piston, so you should be careful. Essentially, just make sure that if your units are, matching or not. Not units will match, but the multiplying factor that comes with the unit. That is one very common mistake that people do in very mock, like multiple mock. I have seen multiple mocks for gate, as well as in subjective exams as well. It happens. I know some of you might think it is not that big of a concern, but believe me, uh, due to negligence, it will happen. So please be careful. And second is modify this uh, as per your problem. So you should be uh, smart enough. You have the recipe now. If your problem is having some uh, let's say different type of string, so in that case this constant will change. That should be provided by the investigate the paper setter or someone. If your piston is having negligible mass, this term will go away. And if there is different pressure than the atmospheric pressure on your system, then this term will also be different. Uh, so let's say if your system, the whole system itself is moving, from ground to a certain height. So in that case also there will be PATM variation, But those are high level things. But if you know basic equation, and if you can modify it according to your need, you should be able to solve most of the problems in this class. So let me just, so yeah, this is the point. So now we have 20 minutes, so I'll quickly go through some problems that I thought we should be aware of. uh, we take, let's say, one simple problem. uh, let's start with a simple problem. You have a piston cylinder assembly. Most of the problems are piston cylinder assembly only in this discussion, so don't worry about it. I'll just draw it quickly. So if you have such a system, and here mass of the piston is given as 5 kg, cross sectional area of piston is given as 5 centimeter square. It's actually it's better to convert everything in SI units initially only when you write given problem per unit physical quantities. And the system has here the mass of the uh, mass of saturated water vapor. I'll call it M. We have G, so I'll call it M. Let's say M only, 1 kg. Uh, so now there is this is the given information, and now the question is, if this system is heated at constant pressure till V2 becomes 3 times of V1. So V2 is the volume of the system at the end of the heating process, and V1 is volume initially. So then what is temperature of the system finally? And take PATM as 100 kPa. So this is your whole typical question will be like this only. In this case, I'll just change my thing. So one thing you should notice is no spring or anything here. So no K delta X business here. So it will become essentially uh, P equal to PATM plus mass of piston into acceleration due to gravity upon area of piston. So now you have MP, AP, G you can, if not given, you can typically assume 10 meter per second square. That's a good assumption in this context. Or if you want to do proper calculation, you can take 9.8 also, but we'll keep it at 10 because that won't have much effect here. So you have everything here. So now one thing you should note is, even if in the question, even if this thing was not mentioned, constant pressure process, this process will be a constant pressure process because the PATM is constant, mass of piston is constant, cross sectional area is constant, G is constant. So if you heat this system from 1 to like process 1 to 2, it will essentially be a constant process, constant pressure process only. So that hint you should take, because if I am going to set such type of question, I will not give you this. So if you have understood that last equation or this form of this equation correctly, you will realize that this will be a constant pressure process. It won't be any other process. That is not possible. So now how will you solve this? Let's say you can calculate P from here. So I'll not go into calculation, but you have 100 kPa. So let's put everything into SI units. You have mass, you have G, then you have the AP, cross section area of piston. So from here you'll get certain P. I leave this numerical exercise to you. And now, since this is a constant pressure process, the P will be essentially equal to the P1 and P2. And now, since the system is heated, the and one more hint here is it's a saturated vapor. So when you look at the steam tables, you can get the specific volume of this water vapor equal to Vg at P1 and V1. I mean, like V1 is not required because it's a two-phase mixture. So if you have P1, you'll get the Vg there, and then if you have Vg at 1, and if you divide it by uh, or multiply, so basically V1 will be mass of the vapor into specific volume of saturated vapor at 1, which will be at P1. So if you do that, you'll get some quantity in meter cube. That will be your mass of the system, because this is in kg, this is in meter cube per kg. Kg will cancel out. You'll get some volume. Now V2 will be 3 times of V1. So you'll get this volume. And now the question is your V2 a saturated vapor, superheated vapor, or a two-phase mixture? So I mean, I will leave this to you to figure it out, but it's quite simple. If you want to, let's just say, if this type of question comes to you, uh, at V1 at point 1, your vapor is already saturated. So if you again heat it, it will definitely be in the superheated region, since uh, if P is constant pressure process. So then what you do, you have P2, which is again P1. And let's say instead of V2, focus on V2 by M, which will be specific volume because steam tables are in meter cube per kg. So if you want to see that, since here mass is 1, it will be same only. So here for this P2 and V2, you go to the steam table and get the T2, which will be T saturated. It won't be T saturated because it's a superheated phase. But here you will get T2 from the superheated steam table. You will not get it from the saturated steam table. You should go to the superheated because your final stage is in the superheated region. One more thing is, uh, like one more hint is, your V2 is greater than Vg because it's almost 3 times than Vg at 1. So it will be definitely in superheated region. So if you do this calculation, I'll not go into the uh, like mechanical part of it. So it will be around 879 degrees Celsius. Should be arriving at this number. So yeah, that's a one problem, one type of problem you will get. And one more thing is, to get T2, many a times you need to use linear interpolation. Why? Because in steam tables, values are discrete. So if you want, let's say in steam table, if you go and if you see, let's say there is certain like uh, specific volume versus temperature plot you have, and at point 1 it will be certain value, for point 2 it will be certain value, and so on. But if you need something in between these two, then uh, you need to do the linear interpolation. I hope everyone knows what is linear interpolation. You you essentially fix or fit a straight line between 2 points and assume the variation between these 2 points will be linear, and this assumption is justified as long as points 1 and 2, which are shown here, are quite close to each other, and therefore you can do it for our application. It won't be giving much error. If these points or the data points in your steam tables are far apart, let's say 100 degrees Celsius apart, then the linear interpolation may not be correct idea. But if it's like the points are, let's say, 10-20 degrees Celsius apart in 800 degrees Celsius range, then it's okay. You can do the linear interpolation and you can arrive at the intermediate values. So these are the important points, and this linear interpolation is required everywhere. Uh, Maybe this assignment you'll not need it much, but if you go to the higher or the advanced concepts using steam table, uh, you will need to do the interpolation, linear interpolation. If you are using softwares like engineering equation solver, EES, which was taught to you by professor in the last week, there you don't need any interpolation because the software itself does that job for you and gives you interpolated or uh, fitted values. But in exams or in competitive exams, you'll not have that luxury. So you should be aware of what is linear interpolation and when it is valid, when it is justified. It's not justified always. So yeah, so this type of problems are there. You can easily tackle them. I'll take one difficult problem and we'll close for today. It's getting late. So let me just scroll through. Okay, we'll take a problem which will have everything. I think similar problem was taken by professor in the class. So maybe if I have some other thing, give me a second to just look into my notes. all are like typical piston cylinder problems. So anyway, uh, what we'll do is, uh, actually I was traveling this week, so I don't know if Abhik has already taught you this one. But anyway, we'll see if we have time. So I'll write down the question for you. Uh, so, so the question is, yeah. So the question is essentially, you again have a piston cylinder assembly, but now you have a spring, you have a piston, and here in the enclosed volume, you have, I think it's a, yeah, it's, they have just mentioned it's a water H2O. They have not mentioned in the question that what is it. Is it a two-phase mixture or uh, superheated or some cold liquid? Nobody, nothing is mentioned. You need to figure it out on your own. So I'll write what all the things that are given at state 1 or the initial state. Uh, P1 is 600 kPa and T1 is 600 degrees Celsius and V1 is, oh sorry, not the specific volume, it's a total volume. V1 is 0.8 meter cube. This is your state 1, and then uh, you then the system is cooled till its pressure becomes 200 kPa. So this is your system, and let me just see if any other things are given or not. Yeah, one more thing is, like, this is not that relevant for this question, but the underlying assumption is that, it is given in the question that spring does not exert any force on piston when A, it is at the bottom, that means here, and B, uh, when the P atmosphere or the outside pressure is equal to P atmosphere, which is 100 kPa. But this system, it is operating at 600 kPa and then coming into 200 kPa. So this assumption, even if it is not given, it's irrelevant because we are not reaching 100 kPa or we are not reaching at the bottom of the cylinder. So essentially, there will be some spring force always present. So this assumption, even if it was not given, it would have been okay. You need to solve this question on your own. So now, to find one, you need to find mass of H2O in the cylinder. That is first. And second, you need to uh, find the specific volume at 2, final state, when P pressure is 200 kPa. So these two questions you need to answer. So let's quickly go through the solution to this problem. Uh, let's say first part. If you want to do this part, you need to first figure out what is your uh, first, what is the state of this H2O at point or at state 1. So if you look at the steam table, uh, let's say if you are having T1 equal to 600 kPa, just look at the T saturation. So one second, if I have steam table, yeah, I'll just check. Or you can do vice versa also, 600 degrees Celsius, if it is there at all. No. So basically your temperature is above the critical point temperature of water. So even if the pressure is 600 kPa, you are way above the temperature of that two-phase region. So it is definitely uh, anyway, let's say if I write it down, if T1 is 600 degrees Celsius, no need to write V1, we'll use it later. So this is a superheated region. Definitely you can cross check from your own steam table. So in this case, to calculate mass, essentially you have volume, which is 0.8. So what you need is a specific volume. So if you divide 0.8 by that value, which will be in meter cube per kg, you'll get your mass in kg. So to find that specific volume, now since we have figured it out that it is a superheated region, you need to go to the superheated superheated state table, and you need to see the pressure, which is 600 kPa. It is 0.6 MPa. If your steam table is in MPa, mine is in MPa, so I have to convert that part. So if you do that at 0.6 MPa and T equal to 600, my specific volume is 0.669. I think it's, yeah, 0.66974. So if you do this calculation, it will be 1.19 kg. So this is your mass of the system. So this is your first part. Now the second part. Second part is regarding the specific volume in the end. So again, here we have a spring on top of piston, and since it's a linear spring, which is what we take in this course, we don't take any other type of spring. So if this is the case, then essentially uh, your pressure of the system is linearly proportional to your volume of the system. Now this is a very tall claim. How I am saying this is because I'll give you an intuitive proof. Your pressure is nothing but the force into or divided by area. It will be this area, the piston area in this case, and this force it is essentially plus P ATM. This atmospheric pressure is there. So this is essentially your total pressure. This P is linearly proportional to uh, the deflection in the spring. And if you write this deflection in terms of uh, let's say volume change of the system, you can write it as volume change divided by cross-sectional area of piston. So essentially uh, this is what this is. So basically in such systems where your spring is linear spring, essentially your system pressure is linear function of your volume of the system. So now you should go to the PV plot. This is a PV, not a specific volume, but it is a constant mass system. So even if you put specific volume on the x-axis, it is fine. It will be same only. So now your system is at. Uh, I mean, the thing is, P equal to 600 kPa, T saturation is, I think, around 160. I just saw. Yeah, it is around 159 degrees Celsius. So, and let's say in the end, if your pressure is 200 kPa, uh, so what my point is, you should your P1 V1 will be here somewhere because it's high pressure, high temperature scene. And when your system has zero volume, you'll end up at PATM, which is given by this assumption. Even if it is not given, you can assume this on your own, and there will be a linear fit to your uh, volume pressure volume change behavior. So your this is your point 1. Let's say your point 2 is here somewhere, which will be having 200 kPa. So now you need to find what is your B2 in this case. So you can do linear interpolation again, and you can, this is V equal to 0. So you have 3 points where you have 2 points where P and V here and here, and you have an intermediate point where you only know P, the V2 is unknown. So since you know how to use linear interpolation in steam table, you can essentially apply it here. So if you do that, it should look like this. Yeah, P1 minus PATM divided by P1 minus 0 equal to P1 minus P2 upon V1 minus V2. And if you solve this, since only unknown is V2, you should be able to solve one equation. So your volume will be 0.16 meter cube. Just remember that if you are using V everywhere, use V. If you are using small v, specific volume, use small v everywhere. So since in this case it's better to use capital V because we know capital V, so that's why it's better to use this for this problem. But in some other problem you can use specific volume also, and from P2 you can get specific volume as P2 by mass of the system. So if you solve, you should get 0.134 meter cube per kg. That's the correct answer. You can try it on your own. I'm just giving you the answer. And yeah, I think we are over the time now. But essentially, what I'm trying to say is, uh, for such type of problems in which you have a linear spring and you have a piston with certain mass and certain uh, cross-sectional area. This is the relation that is the, you can call it as a governing equation in this case, but this is the equation that you should use, and use your basic knowledge of steam table, figure out where these states are. If you are not comfortable, uh, just go back to your basics, draw PV plot or TV plot, whichever is relevant to that problem. Check your units and modify this problem according to your uh, problem statement. Modify this equation. So yeah, in the last problem there was no weight of piston. Even if it would have been there, the variation will be still linear because your piston weight will again add some constant to this extra force term, because your piston weight is constant, it's not variable. So essentially, even if in this question, even if this piston had finite mass, you will solve this problem in a similar fashion, because this mass essentially results in certain force acting on the system which will be a constant. It won't be changing with the deflection in the spring. So essentially this uh, pressure of your system will be equivalent or directly proportional to the volume of your system or the specific volume. So this is how you should do it. And And yeah, I think we'll stop now because we are above our time. And yeah, I'll share these problems or these notes with you. Please take a look. Based on this, you may be able to solve your assignment 2 problems with ease. If not, we'll discuss some in next class. So yeah, before stopping, if anyone wants to ask anything, please go ahead or we'll close. So 1 second. Where do you see it? Hmm. Gibbs free energy significance and all. Okay. By ideal gas, we can say T2 is equal to 3T1. Okay, I think this was regarding the first problem. Hmm. I mean, yeah, you can say this, but in that case, you need to assume that water vapor is an ideal gas. Uh, you have to check how much that assumption is justified, because if I think you are not there in the last class, we discussed about ideal gas equation. If your the temperature of the gas or the temperature of your gas is too high, or if the pressure is too low, then you can assume it as an ideal gas. If it is not, then it is not a good assumption. So yeah, you can assume it, and you maybe get away with it for some time, but not always. So please make sure that you are not using ideal gas equation anywhere, especially if there is a multiple phase like liquid vapor mixture and all. The ideal gas you can't use. If it's a single phase problem and if your temperature is high and pressure is low, you can use ideal gas equation. But I would say for such type of problems, such a piston cylinder, constant mass or fixed mass systems, no need to go to ideal gas unless and until you are not provided with the sufficient data. Otherwise, such problems are, you should be able to figure it out on your own without ideal gas, I feel. But anyway, and this gives free energy and all. It's uh, it's an advanced concept. It will come. I think in between I told you there is something called as chemical equilibrium. When you say your system is in equilibrium, it's in three equilibriums: physical, mechanical, thermal, and chemical. So essentially, Gibbs energy comes in that part, not in this mechanical equilibrium part. But yeah, Gibbs free energy, I'll try to discuss when this concept becomes relevant. I think it's too early for Gibbs free energy, assuming that you are a beginner, since this is the undergrad level course. Uh, Gibbs free energy, it's an important concept, but not at this point. So we'll discuss when we'll get there. But let's just say at this point we'll not go there. So I think yes, you should join that class. Maybe we'll discuss more about it, because you need certain prerequisites to understand what is Gibbs free energy. So if you don't have that, you'll not be understanding it properly here. So yeah, I think these two were the questions that have been asked. Uh, Anybody else? I think people are leaving already. So I'll also stop now. Uh, I'll share this video and link with you in some time. Sorry, link to video and notes. And yeah, we'll meet in the next class on Tuesday. So I'll stop recording now. And yeah, thank you all for attending, and we'll meet next time. Okay, bye and have a good night.